So let's discuss about turbo machinery. Okay, so here we'll basically discuss about the pumps. To begin with, we'll discuss with pumps. Okay, so what is pumps? Pumps are the devices which consume energy and resulting in increase in the fluid pressure, not necessarily in the speed. So all this we term as increase in the head of the fluid head. So head is nothing but your energy per unit weight, per unit mass or unit weight, whatever you want to call. That is how you express the head. So pumps are the devices which take energy and then increase the energy of the fluid, energy content of the fluid. So if you have flow in here and flow out, so energy content of the fluid, let's say it's E in here and E out here. You supply the work to the pump by connecting it to some motor. The work which you give increases the energy of the fluid, and the difference in the energy levels is nothing but the work supplied. So this is just a simple energy balance. So the output, so that's what happens. Okay, now the pump terminology when used with gases, it is called fans or blowers or your compressor when it is used with, I mean the same terminology when you use for gases. Okay, okay, they also work on the same principle. Increase and increase the pressure rise of the gas. That's it. Okay, but our topic here is to discuss about pumps. So they are broadly classified into two types. Pumps are broadly classified into two types: reciprocating and rotary pumps. Well, reciprocating, they work on basically just like your IC engines, but in the reverse way. You have a reciprocating piston in a cylinder, and because of the work done on the piston, it compresses and increases the, it basically tries to decrease the volume and increases the pressure rise. So just like your IC engines in a reverse way. Okay, and rotary pumps are what we have mostly in the syllabus. So we'll discuss a great detail about rotary pumps. And so let's start with rotary pumps or your centrifugal pumps. But let's classify first on the rotary pumps. Okay, so what you have is you have two kinds of, I mean, depending on the, if you want to look at the geometry, you have two times two devices, basically an impeller and then the outer casing. Okay, so let me just draw it here. So you have an impeller and you have an outer casing. Okay, and the impeller is connected to the shaft. Okay, so the inner is impeller and the outer is some kind of casing which is mostly stationary. Okay, to change the direction of the flow, stuff like that. Okay, so impeller is something which is your something like rotor, which is the rotating component. So this I'm broadly telling you how a typical how a typical centrifugal pump will look like, or actual pump. You'll have an impeller and a casing. Impeller is the rotor part, rotating part. Casing is your stationary part. And now, so these kind of pumps you can say rotor dynamic pumps, and basically impeller is that component which imparts the momentum to the fluid. Okay, and now depending on the flow, how it enters and how it goes out, you have this centrifugal pump, you have the axial pump, and you have the mixed type. Okay, so centrifugal pump, well, fluid enters in all this, the fluid will be entering uh, at the inner dia and goes out the outer dia. So in the centrifugal pump, fluid enters axially along the shaft, parallel to the shaft axis, and discharges radially outwards or tangentially along the outer radius. Okay, in axial flow, well, the flow enters and leaves axially. So let's now discuss about the centrifugal pump. Okay, so let's draw a 3D view how it basically looks like. So the impeller, a typical impeller will look like this. You have a lot of vanes mounted. So this is something like this. Let's say two vanes mounted like this. So these are two vanes. So mostly the flow enters radially, and then either depending on the direction how it is bent at the outwards, it either leaves tangentially or it basically leaves radially. Okay, so what we do is we consider the top view. Okay, let me draw the view here. So you have the inner dia and you have the outer dia. Okay, and let's say the rotation direction is in this. Okay, and the vanes, one of the vanes is like this. Okay, so the flow enters. So there are a couple of things. First we use backward. This is how the vanes look like. Okay, they are backward to the direction of, so you have these backward inclined blades. Okay, that is, if the direction of rotation is like this, the vanes bend opposite to that. Okay, so this is how, why we use this is because of they give higher efficiency than the forward inclined vanes. So this is default. So that's the reason why backward vanes are used. So now let's draw velocity triangles, and one thing is that fluid flows in into the blades at the inner dia, at the inner circumference you can say, or the inner periphery you can say, and flows out radially at the radial outer circumference. Okay, so let's say it is rotating with omega. Okay, so now if I happen to draw, so one of the veins is like this. Okay, so let's say the inner circumference is this, outer circumference is this, the inner dia. Let's say if I unwrap this. Okay, so the vein is something like this. Okay, and this is the direction of motion. I mean, at this point, if I unwrap, this is the direction of motion. So I'm just drawing the velocity triangle. So this is the direction of motion of your okay. Okay, so how does this move? So this angle, okay, let's write down with the nomenclature beta 1 and beta 2. Beta 1 is the blade angle at the inlet or in at the inner periphery. So this is your inner periphery or the inner circumference, and this is your outer periphery. Okay, so blade angle at the inner periphery, beta 2 is blade angle at the outer periphery. Okay, so as it is rotating like this at this point, so this is how the fluid enters. You have relative to the blade, always the fluid will enter tangential, right? I mean, if you imagine that if you are sitting on the blade at this point, so flow will be just tangential to the blade as observed by an observer on the blade. So flow will be along the blade angle, and this angle is beta 1. That means the tangent of the blade, the inlet, will make with the circumference beta 1. So this is the direction of the relative velocity at the inlet, and u, that is the direction of motion. I mean, the u is the velocity of the blade tip. Remember, the entire thing is moving with omega, that is angular velocity. It's a fixed axis rotation about the center. The velocity of the blade is u at the inlet, that is r1 omega 1. It's basically any point on a body which is rotating with omega 1 has a velocity r1 omega 1, where r1 is the distance from the center of rotation. So that is u1, and that can be represented like this. So your u1 plus vr1, that is at the inlet, your u1 is this way, vr1 is this way. U1 is the velocity of the tip, vr1 is the velocity of the fluid relative to the tip. So the resultant of u1 plus vr1 is the absolute velocity of the flow of the fluid relative to the ground. Most of the times this is tangential. I mean, sorry, this is most of the time it doesn't have any tangential component. The flow absolute velocity is such that the flow enters perpendicular to the inner periphery, and this is your blade angle. Okay, so this is your inlet. So this is the inlet velocity triangle. Okay, now at the outlet, this is how it goes. The relative velocity is like this, tangent to the blade surface at the outlet. Okay, and this is your beta 2, how much the tangent mates with the blade. So at the outlet, your vr2, that is relative velocity at the outlet, is in this way. Okay, and your u is always in this time because this is the direction of rotation. So this is your blade tip velocity, which will be higher than u1 because it's radially outwards. R2 is more, so u2 is r2 omega 1, and joining this relative velocity with respect to the tip plus velocity of the tip will be your absolute velocity, which is v2 at the outlet. Okay, and this angle is what is beta 2. Okay, so now what I will do is this is u2, let me write it here. So V2, if I resolve, you have one tangential component V2. V2 has two components. If you resolve along this, V2t and V2n, which is the normal component. Okay, so this is the velocity triangle at the outlet. Outlet velocity triangle. Okay, so now this one. So a couple of important points here. First is the torque applied on the impeller basically changes the momentum or imparts the momentum to the fluid. So torque applied on the impeller is rate of change of angular momentum. This comes from your angular momentum equation, rate of change of angular momentum. So just like your linear momentum, we express this rate of change of, just like your force was rate of change of linear momentum, your torque is rate of change of angular momentum. So angular momentum at the outlet is mass of flow rate at the outlet, velocity. Now obviously the tangential component, what is angular momentum? Angular momentum is moment of linear momentum is your angular momentum. Okay, and now so obviously the one the velocity, let's say at the outlet is v2, so the tangential component is this v2n, the normal component is this v2n. So the tangential component only will have a moment about the center. The center is somewhere here. Obviously v2n passes through the center because anything normal to a circle will always pass through the circle center. So it doesn't produce any moment. So only V2n produces. So V2n, V2t into R2. So this is the angular momentum MVR of the outlet and inlet. So this is in the direction of rotation, and this is how you apply the torque. Torque is applied in this direction. So your the final angular momentum also in this direction. Okay, minus the initial angular momentum. Well, initial tangential you don't have any component, but even if you have, and let's say that is rightward, so you will write m1 v1 t r1. Okay, so this is the torque applied on the momentum on the impeller. So m dot is the mass flow rate, which we assume it's constant. So mv2 r2 minus mv1 t r1. This is the general expression. Okay, so how do we now write the torque? So the torque would be mass flow rate, which is rho density into volume flow rate, into your v2t u2 minus v1t u1, and that we can express in omega angular velocity. So r2 omega 2 minus v1t r1 omega 1. So this is the general expression for the torque. Now the power delivered to the impeller is torque into omega, and that is okay. So the torque was, sorry, there was a mistake there. This was r1, this is r2, this is r1. If you compare with the previous slide, the previous thing, and this is r2. Okay, so how do you write this? Let me just write torque is rho q v2t r2 minus v1t r1. So this is what the torque. Now the power applied is t omega, which is rho q omega v2t r2 minus v1t. This is in a general sense I am writing. Okay, so omega you can take inside, and r2 omega will become u2, r1 omega will become u1. This is the power. Now the head supplied or the head increased, and the fluid is head supplied by the pump, by the impeller to the fluid. It's nothing but the power by the weight mass flow rate into g. So what was the head? Always when we represent, this is the head, velocity head, this is the pressure head. Each of the term is basically the energy per unit weight. okay, because it's half mv square, so you have divided with the mass and also you're dividing with the g, so it's energy per unit weight. That is what is head. And what here we are doing is power is the energy per second, and we are dividing with mass flow rate into g, so to get head. So this becomes rho q v2t u2 minus v1t u1 by mass flow rate is density into volume flow rate by g. So this becomes v2t u2 minus v1t u1 by g. So this is the head supplied by the impeller, a general expression which we derived based on power. Based on your rate of torque applied is rate of change of angular momentum of the fluid. Now a visit to the velocity triangle help you again. This was u1, this was your vr1, and this is your v1. So there was no tangential component, there is only normal component which was v1. This was at the inlet. At the outlet you have vr2, you have u2, and you have v2. Okay, so this was your tangential component v2t, and this was your normal component v2n, and this is your beta. So couple of expression here. Okay, so how do you find out v2t? So obviously the tangential component is your, if you happen to get vr2, okay, the tangential component is your, in terms of vr2, it is vr2 cos beta is your vr2, okay, cos beta is this, okay, and u2 is bigger than that, so vr2 cos beta, okay, so your u2 is, entire thing is this u2 minus your, so u2 is the total thing, u2 minus vr2 cos beta is your tangential component, and the normal component is your vr2 sine beta. Okay, so this is about tangential and this is about the normal, both for the inlet and the outlet. Now a word about volume flow rate. The volume flow rate at the inlet is, if you recall that entire figure, this was the inlet and this was the outlet. Okay, so this periphery is 2 pi r1 into, let's say b1 is the width of the blade into the paper, b2, so b1 is the width of the blade into the paper at the inner radius, and b2 is the width at the outer circumference. So the area of cross section is 2 pi r1 into b1. So the area of cross section is 2 pi r1 into b1 into the normal velocity is what matters to the flow. So this is at the inlet. At the outlet, again the same thing, 2 pi r2 b2, the tangential component v2, so this is how we express flow rates at the inlet, and both are same, so you can just equate. So this is how, so two things, one is the expression for the head develop, and the second thing is how do you express velocity triangles. So once you are able to write down velocity triangles, then you can express tangential and the normal component, and once you are able to express tangential and the normal component, then it's all about getting your, then it's all about getting your the blade angles. So the blade angle at the inlet is beta 1, at the outlet is beta 2, okay, and this is beta 1, okay. So this is all about so once first is drawing velocity triangle, the second is writing the head expression. So we'll do a problem on this so that all these relations will be covered. Let's do a problem. Hmm. Hmm. Right.